What's going on, everybody? In this video, we're going to be talking about Rolle's theorem and mean value theorem. These are two theorems that you're going to need later on for certain proofs in calculus, but before we even get to that stuff, we need to know what these two theorems actually are, right? So in this video, we're going to start by talking about what Rolle's theorem is, followed by what mean value theorem is. It's not going to take me too long to explain what these two things are because, well, they're really quick to explain. They're not that complex of ideas, okay? And then we're going to get into the practice. We're going to, when we have theorems, we want to verify them. We want to know that they're true. And so we'll use some different examples and we'll show that both Rolle's theorem and mean value theorem will hold. Okay? We'll also do kind of the opposite of that. We'll prove that there is no contradiction. So given a specific example that seems like it violates Rolle's theorem or mean value theorem, we'll show that there is no contradiction. Okay? And then another thing that is definitely something you talk about with Rolle's theorem and mean value theorem is proving that a certain number of roots exist, right? Roots meaning like the roots of a quadratic. Now, as always, I have the PDF for both the unfinished and the finished notes in the description down below. The unfinished notes, I think, are the best because you can fill them in as you go. And, you don't have to spend too much time worried about, jotting down all the wording that you could just read for yourself. Now you'll be just taking the notes on doing the math part, right? And I feel like that's just going to be a little more efficient for you. And I also have those finished notes if you're just looking to review. Now, before we get into this video, I quickly want to mention my full Calculus 1 course, which I'm going to have linked in the description down below. In this course, I have a bunch more practice problems to really get you feeling confident with each topic. I also have video explanations for every problem in the course, so don't worry, you won't be left in the dust on anything. So if you're interested in that, make sure you check out the link in the description down below. Now let's get into this video. Now let's start with Rolle's theorem here, and here is literally all Rolle's theorem is saying. Let's grab 2 points here. Okay, we're going to put 2 points. We're going to put them right on the x-axis. Okay, and we're going to have one at x equals a and one at x equals b, and we're going to draw a nice smooth curve that connects these two guys. Okay? All Rolle's theorem says is that, look at this curve here, right? It starts by going upwards and it ends by coming downwards, right? So these guys are all positive slopes, right? If you draw any tangent line to the graph here while it's going upwards, it's going to have a positive slope, and here it's going to have a negative slope. But notice that it's going to have to, if it wants to come back down to the same y value, it's got to turn around, right? And so let's draw a tangent line here. Let's do it right here. This looks about to be the turnaround point. We'll call that x equals c, okay? And drawing a line here, if I can draw a nice clean one there, actually, that came out pretty well. What Rolle's theorem is saying is that this curve at some x coordinate, we'll call that c in this case, the slope will have to be 0, right? Because it has to turn around going from positive slopes to negative slopes, or you could say the exact opposite if the curve went this way, right? But it's got to happen at least once on this line, okay, on this curve. And that's not something that only has to happen when you are on the x-axis, right? You could have these points be off the x-axis a little bit as long as they're at the same y value. As long as you're starting at the same y value that you're ending at, if you go up, you gotta come down, and that means that you have to turn around at some point, and the slope will have to be 0. That, my friends, is Rolle's theorem. Okay? And so, just saying this a little more rigorously here, Rolle's theorem says if you have a function where the two y values at a and b are the same, and you have a continuous curve, right? There's no gaps in this curve right here. We can see that. And we have a differentiable curve, which means it's smooth, right? There's no corners in it. Like, it doesn't look like y equals the absolute value of x, right? Then there has to be some kind of x value here where the slope of the curve at that point is 0. Okay, it's got to turn around. That's Rolle's theorem. Now let's move on to the mean value theorem. And the mean value theorem is basically saying the same thing, just a little more general, meaning a little more like broad is what I mean. Okay, let's draw 2 points in space. Okay, so now we're not just going to be at the same y level, we're just going to move the second point up a little bit. Okay, or just at some other y. And I'm going to make these points orange because we're in the orange section. Okay, we'll make this point at x equals a and this point at x equals b. Okay, and let's draw another curve. Okay, we're going to draw another curve that connects these two. All right, awesome. So now what the mean value theorem says, it's basically the same thing as what the Rolle's theorem said, just now it's almost like a rotation. Actually, it is a rotation. So we're going to draw a secant line here. What a secant line means is it's a line that's going to pass through both of these points here. Okay, and I'm going to make this just a little nicer to look at. Here we go. Now it's really passing through each point. Okay, this is a secant line, so I'm going to label it as such. I don't think I knew what a secant line was until I came to calc. Maybe you already know what it is, but yeah. So now it's kind of like the same thing that we were dealing with before. Think about this entire thing as being rotated. Let's just rotate it like that. Now, doesn't that look like the same thing, right? This graph and this graph, right? What it's saying is that now this guy is kind of like your x axis, right? It's kind of like that horizontal line from before, right? And it's saying, well, you're going up again, you're coming down, you have to turn around at some point, right? You have to have a slope of 0, but it's not 0 here, okay? But this, what it's saying is the slope needs to be parallel to the slope of that secant line. The secant line before was the x-axis, right? Now it's just some other line in space, but the same idea still applies. These slopes need to be equal at some x value along this curve. Now let me rotate it back because you're probably tired of looking at this thing by now, being all weird. Okay, let me just it back there, nice. And you see the reality of what we've just created. Here's your C. Okay, this is now the x coordinate where the slope of your curve is equal to the slope of your secant line, right? It's the turning point where you stop going away from your secant line and you start coming back. Okay? That's the mean value theorem. So saying that a little more rigorously, a little more gross with big words, if f is continuous, or if f satisfies the following, if it's continuous, which it is, okay? If it's differentiable, meaning it's smooth, okay? Then there's some x value where the slope, the instantaneous slope, right, the derivative of the curve is going to equal, and this is just, you know, the classic delta y over delta x, right? I know that it gets a little confusing when you start seeing f of b and f of a, but really that's just y2 minus y1. All right? And so it's saying that it will equal the slope of your secant line. That's mean value theorem. Now let's move on to some practice problems with that. Okay? This practice problem says find all values c that satisfy Rolle's theorem in the equation f of x equals 2x squared minus 4x plus 5 from -1 to 3, right? That's our x interval here. Okay? So we're trying to find those values of c now where we have, we're dealing with Rolle's theorem here, right? We're trying to find those values of c where we have our turning point, where we have our derivative of 0. But the first thing we need to do is, well, establish that the 3 conditions are correct. We need to make sure that we have that the 2 y values are equal, right, at the start of our interval and at the end of our interval. So let's do that first. So that's going to be 1. Okay, I don't know why I usually don't write my 1s like that, but okay. Right, I write them like this. Let's look at f of a first, or f of -1 in this case. Plugging that into this function, we get 2 times negative 1 squared minus 4 times negative 1 plus 5 equals what? Well, we have a 2 times 1, that's 2. Okay, and then we have a 4 here. So we have 2 plus 4 plus 5. That is going to be 11. Okay? And all we have to do now is make sure that f of 3 is the same thing. F of b, right, is 3 in this case. And so we plug in 4x, same as we were before. And again, we are going to get 11 here. Watch this. You're going to get a 9 times 2, that's 18. You're going to get a minus 12 plus 5. And again, you're going to have 11. Okay? And so the first condition is satisfied, right? So we could say satisfied. But what about the second condition? Is this curve going to be continuous? And is it going to be differentiable? Well, let's think about this, right? We're dealing with a polynomial here, right? And we're dealing with, x's to powers. There's no place where this thing is going to be discontinuous. There's no place where this thing is not going to be a smooth curve. So yeah, to both of those, we're going to pass those two with flying colors. Okay? And so now the goal is to find the x values, right? The x values that we'll call c, right? These special x values are what we're calling c, where this derivative is 0. That's what Rolle's theorem is, right? It says it right here. So now we're going to, I'll say, verifying or finding the c values. I'll write that instead. Just to organize this a little bit more. I'll probably say that and I'll organize this once, and then like in the green section, I'll just completely abandon that and make it messy. So taking our derivative here, right? We know that our function is this guy. I'll duplicate that, bring it down. Looks like I'm dragging a y with me. Taking our derivative, we're just going to do a little bit of power rule here. We're going to get 4x minus 4, right? And the derivative of this guy is 0. To solve from here, you can factor out a 4 and just divide it away. And I'll stay on this page here. You can divide that away to get 0 equals x minus 1, right? And if you just add 1 on both sides, you get that x equals 1. All right? Now, is x equals 1 on our interval? Right? That was the whole reason why we did this. Rolle's theorem, since this function passed these 3 conditions on this interval, right? It passed the 3 conditions on this interval. It means that there needs to be some x value where the derivative is 0 on this interval. So do we have a value, a x value where this derivative is 0 on the interval? Well, we found one at x equals 1, and sure enough, x equals 1 is on our interval. Okay? And so that's good, right? We've done our job. So moving on to verifying the mean value theorem now. Now we want to find all values c that satisfy the mean value theorem in the equation f of x equals the natural log of x on the interval from 1 to 4. And as a hint here, I said verify the 2 conditions first, because that's really what you need to start off by doing. We're going to look at our 2 conditions here, and basically it's continuous and differentiable, so it's 1 less than we had before. And the reason why it's 1 less, by the way, I'll just go back to that quick. The reason why it's 1 less, why we don't have the f of a equals f of b, is because Rolle's theorem is just a special case of the mean value theorem when this thing is completely horizontal. Right? If we have a case like that, that right there is Rolle's theorem. Right? And so if you have that f of a equals f of b, you're dealing with a special case of mean value theorem, which we call Rolle's theorem. Okay? Awesome. So now let's see that this function is going to pass our 2 tests. Is it continuous and is it differentiable? On this interval, of course. And you might look at this and be like, well, natural log of 1, is that undefined or anything? Like, is that all right? Like, I know you can get a little sketchy there, but natural log of 1 is just 0. Okay, it's only when you start getting into natural log of 0 and natural log of any negative number, both those things are undefined, right? And so that's where natural log starts to become discontinuous and non-differentiable, right? Because you don't get any points there. But we're dealing with positive numbers of natural log here, right? Natural log of positive numbers. And so it's going to pass both these tests with flying colors. Okay, it's a nice smooth curve, right? It looks like this guy. And what we're going to be doing with this curve is we're going to be calculating from, let's say this is x equals 1, okay? Let's just draw it right here like this. Say that's x equals 1 and that's x equals 4. We're going to take the 2 points, and we're going to draw a straight line that connects them, right? We're going to find the slope of this line, and we know the slope of this curve is going to have to equal the slope of that secant line at some c value, right? And or at some x value, which we call c. So we need to find the slope of that secant line first, and then we'll find the slope of the tangent line. Okay, the derivative, right? And so starting off, the slope of the secant line, that's just going to be the regular equation for the slope of a line. And really all this entails, I know the function notation is gross and annoying, but we're just plugging in, a and b into the natural log. So we're going to get natural log of 4 minus natural log of 1 over 4 minus 1. Now, natural log of 4 is just going to be subtracted by basically 0 here, right? So we can leave that as natural log of 4, and then in the denominator we have 3. Really don't need to put that in our calculator yet if we don't want to, but you can. So since we've passed our 2 conditions here, we know that this natural log of 4 over 3 is going to have to equal the derivative of natural log of x, which is 1 over x. It's going to have to equal that at some x value on this interval. And we can find that. All we have to do is set these two things equal to each other. Okay? And see what x value we get. So, setting f prime of x equal to m, which is basically what it says to do here, right? We have f prime of x, so using x instead of a c here, because c is kind of just denoting the specific value that makes it work. It's kind of weird with the notation there. Don't get too worried about that. But on the right hand side there, you have the slope of the secant line, right? That's m. So we have f prime of x equals m. And so f prime of x, that is 1 over x, and that's equal to natural log of 4 over 3. We can just solve for x by, if you want, you can move the x up here, move the 3 here, move the natural log of 4 down here, whatever. I feel like that's just going to be annoying. We'll just put each side to the negative 1 power. Like, we'll flip each side, right? And we get that x is going to be 3 over the natural log of 4, which now, if you want, you can put that in your calculator, and you get 2.16. Okay, you get x equals 2.16. Now, is 2.16 on our interval? Yes, it is. And so that's great, right? Mean value theorem is completely verified here. Everything works for this problem. And so that's it. Okay. So now let's move on to a different kind of example, which is proving that there is no contradiction in one of these theorems. In this case, we'll talk about Rolle's theorem here. This problem says, let's say f of x equals 1 minus x to the 2/3 power. Through plugging into this function, you'd be able to see that f of negative 1 equals f of 1. However, there's no x value c in negative 1 to 1, where f prime of c is 0. Right, so it looks like there's a bit of a problem here, right? The derivative isn't 0 on this interval. And so we know that the endpoints work, right? The first condition works, we're given that. But for some reason, this conclusion doesn't work here, right? And so we're asked, well, does it contradict Rolle's theorem? And so we have to explain about that. Now, I'm going to give you the short answer here, right? Nothing is going to contradict mean value theorem and Rolle's theorem. It's not going to happen, right? Or else you wouldn't be learning about these theorems in class if they were wrong. So what's going to end up happening here for literally every single problem is there's going to be a issue. There's going to be one of these conditions that your function doesn't pass. So this curve could be discontinuous, or it could have a kink in it, right, making it not differentiable. And that's what we're going to find here. So let's just look at this function here, right? This function already passed the first condition. So we're going to say, okay, yeah, it passes 1. But what about it being continuous? Right? What about it being differentiable? Well, first off, I mean, this graph is, oops, my bad. There, that's a better 2, and I'll also write 3. Now this graph is really just a polynomial, right? It's a x to the 2/3 power. It's not going to be discontinuous anywhere, right? That wouldn't really make any sense. That's not what we've actually even talked about this with different like limits and stuff, right? This was one of our theorems, was that when we talked about continuity, right? When we're dealing with a polynomial, it's going to be continuous everywhere on its domain, right? And this thing will go from -infinity to infinity, and on the x direction, and you'll still get a y value in return. So this thing's continuous everywhere. Okay, if you're confused on that, go back to the continuity section when you talked about limits, and you'll understand what I'm talking about. Okay, so in item 2 here, we know this thing is going to be continuous, and you might start to get a little head sweat going on here. What's, you know, this is problematic. We need to get a no for the third condition. And looking at this guy, right, it really doesn't look easy to tell whether this thing's going to be smooth or not. We need to look at the derivative, right, and see if there's any place where this derivative is going to be undefined. Okay, making this thing non-differentiable. And, well, to do that, we take a derivative. Doing power rule on this guy, we're going to get a -2/3, right? We bring that 2/3 out front. And then we have an x to the, well, subtract 1 from that guy, and you're going to get -1/3. Right? And so this, I mean, look, this thing looks gross to look at right now. You have an x to the negative power with a fraction in it. It's gross. So what we can do to really examine this a little bit better, and what I recommend you do in any problem, if you're having trouble looking at something because of a fractional or negative exponent, write it in a radical form, right? Write it as, instead of writing this as a exponent, right, or a fractional exponent, write it as a root. So we can write this as -2/3. This negative is going to put the exponent down to the denominator, and this says a cube root of x. Right, that's what the 1/3 power says, is a cube root of x. So looking at this guy now you can probably see what's going on. We can get a 0 in this denominator, right? Because x is in the denominator. That's problematic because, well, in the case that f prime, or in the case that we're dealing with f prime of 0, which is on our interval from -1 to 1, this thing is going to be -2/3 times the cube root of 0. And that's undefined. Right? This entire denominator just becomes 0. And I can even write out an extra step if you're confused on that. -2/0. And so the third condition is not satisfied. And so the reasoning, right, we could say, here's my little paragraph here. This problem does not contradict Rolle's theorem because it does not meet, or you could say, actually, how about this? Because it is not differentiable along the given interval. And if you want to sound really poetic and really smart here, you could say, thus, Rolle's theorem doth not apply. I'm not going to say doth. I don't like how that D looks. All right, and there you go. Actually, I just got that in the perfect amount of space before the next section starts. Okay. So now we're going to move on to our last topic for this video, which is on proving that a certain number of roots exist for a specific function, right? We want to see, given a function, how many roots does it have? We want to see, for this example, given that 2x plus cosine x, we need to show that it has exactly one real root. Okay, we need to show that it crosses the x-axis one and only one time. Okay, so how do we do this? Well, we're going to use Rolle's theorem in this because, we're dealing with things that are going to be at the same y level, those being zeros, but we're not even going to get into that yet. First, let's just find a interval that has a root between it. Okay, we can do that the way that I like to start off with these problems is just by plugging in 0 for x. The reason why I'm going to do that, I want to see if what I get for this guy is going to be positive or negative. Because I know that if it's positive, right, I'm going to want a negative piece too, because with the intermediate value theorem, remember that, right? I know that it's going to have to cross the x-axis because, as you can see here, we're dealing with a completely continuous function. Okay? So, great. Let's plug in 0 first. And I think I just plug in 0 because it's the easiest thing to plug in. In plugging in 0, we're going to get 2 times 0 plus cosine of 0. And we know that 2 times 0 is 0, cosine of 0 is 1. So h of 0 is 1. That right there is positive. So we're going to want something that's negative. And so the question is, what's the next point that we're going to plug in? And well, I would say that it's definitely, it's up to you, but you definitely, to give yourself a better idea of what point to plug in, look at the function that you're dealing with and be like, okay, well, I want now a negative number. Which way should I go? Should I go, more towards the negative numbers or more towards the positive numbers, right? The positive values of x to get that negative value for y. In this case, I know that as x goes negative, this whole piece is going to go negative. And if I plug in the right x value here, I'm also going to get a negative out of the cosine. And so, honestly, just to give a good number that'll work with the cosine, I'm going to plug in negative pi. Right? It's a negative number, so we know that this piece is going to be negative. And negative pi, right, the cosine of that is going to be negative 1. Right? That's the same thing as the cosine of pi. So we get 2 times negative pi plus the cosine of negative pi, which is negative 2 pi minus 1. And that right there is negative. And so, by the intermediate value theorem, we know, by the way, if you want to review the intermediate value theorem, I definitely recommend it, right? We're saying that if something is continuous, right, then if you have a point up here and a point down here, it's going to have to cross the x-axis. And I mean, that's the specific case that we're dealing with here, but yeah, that's it, right? So by the intermediate value theorem, we know that there will be a 0, or that a 0 will occur between, we could say, between negative pi and 0. Okay? So we know there's going to be a 0 in there. Now, how do we show that that's the only 0, that that's the only real root? Well, that is where Rolle's theorem can come in. For Rolle's theorem, remember the conditions. I can even drag down this guy here. And I'll have to change the colors. Guys, I need to spend time doing that because apparently I have neglected to. And finished. All right, looks a lot better now. So what we can do now, we know that if we have two places, right, we'll prove that this thing is the only 0 by contradiction. We'll say, okay, there are 2 points on this function, and here our function is h, so I'll actually use h instead. Okay, there are 2 points where your y is going to be 0. Okay, now we know that this thing is continuous, right? So it passes 2. We know this thing's differentiable, and I'll talk about why in a second. This thing is differentiable because you can easily take a derivative of that. You can take a derivative here. It's going to be 2 minus sine of x. Right, and this is going to be completely continuous as well for all values of x. So that's pretty nice. So we're all good there. We're dealing with a continuous curve, a smooth curve, and we are saying that there's going to be 2 points where your y is going to be 0. So then what Rolle's theorem says is that there has to be a x value where you turn around, where your slope is 0, right? Where you go from going upwards to going downwards. So let's see if there is that actual point. So how we can do that, remember I just talked about what the derivative was, but I can write it again. We know that h of x is 2x plus cosine x. H prime of x, the derivative, is going to be 2 minus sine of x. And if there was a turnaround point, the slope would have to be 0. So let's see if there's any solutions here. What I'd like to do at this point is add sine x to both sides. And there you go. You get that sine of x is equal to 2. And hopefully you can see at that point that no, that's not going to happen. I can't get my hair out of my face. Sine of x cannot be 2. It's between -1 and 1. That's it. Right? So no output of sine can be anything that's not negative, or anything that's not in between -1 and 1. Okay? So we can see here that there is no solution. And since there's no solution, right, since there is no x value where h prime of x is 0, and there is a real root between -pi and 0, we know there is only one real root. That's what I would say. These are the two things that we found. Okay, we found that there at least, there at least was one root, but there's no turnaround point. And so there has to be only one real root. And so that would be the reasoning that I would write there. My reasoning, my sentence structure, I guess, is not always the best, but it does the job. Oh my god, I need to stop. All right, no more ovals. This is the time. This is the time. We got this. Yes. So yeah, that is going to wrap it up for this video. I hope this was able to help you. Remember, if you're interested in that full Calc 1 course with plenty more practice problems, definitely check it out in the description down below. But that's all I got for you guys, so I'll see you soon.